Hello students. So in this video I will be discussing about step response. In the previous video we discussed about the problems, properties of LTI system, and we took some problems on those properties. So that is to verify whether the given system is causal, stable, um, memory or time invertible or not. Okay, and we took some problems on that. So in this video, I'll be discussing about step response. Okay. So what is step response? So step response is an output due to a unit step function as an input signal. So that means if you consider this as a system, it might be an LTI system or any kind of system. So if your x of n is, it is if the input is unit step function, then the output y of n will be the step response, and here h of n will be the impulse response of the system. Okay. Now this step response is usually denoted not by y of n, so it is represented in terms of s of n. So therefore we can write it like this: h of n convolved with u of n, or u of n convolved with h of n. So s of n is equal to h of n convolved with u of n. Now if you apply the convolution sum expression, so if you elaborate this, k varies from minus infinity to plus infinity, h of k u of n minus k here. Now this u of n minus k will be 1 for n minus k greater than or equal to 0, and it will be 0 for n minus k less than 0. So if you simplify this for k less than or equal to n, and this will be for k greater than n. So that means for values of k which are less than or equal to n, u of n minus k will be 1, and for values of k which are greater than n, so this u of n minus k will be 0. So that's why the limit here minus infinity to plus infinity. So this limit changes from, as I mentioned, it is varying from minus infinity to plus infinity, but this will be present for values of k which are only less than or equal to n. So that means the limit now will become summation k varying from minus infinity to n h of k. So this is the expression for step response in discrete time system. Okay. Now we can express the same in terms of continuous time system, where the summation will be replaced by integration. Okay. And let's take that. Similarly, for continuous time system, so we represent s of t is equal to integral of minus infinity to t h of tau d tau, and I think you no need to put this brackets twice. Okay. So now this is the expression for continuous time system, and this is the expression for discrete time system. So this is how we represent step response. So you have to remember this: for a step response, the input should be unit step function. So even though while expressing this impulse response, it will be in, usually this u of n will always be included with this one. Okay. Now looking at the expression here for discrete time system, so we can say that step response is nothing but the running sum of impulse response. So you can express step response as the running sum of impulse response, where h of n represent impulse response here. Okay. So, and I will just rewrite the definition once again here. So, what is step response? Step response is, it is defined as the output due to a unit step input signal. So, this is the definition of that, and we have expressed this step response in both the discrete time and continuous time. Okay. Now, let's take some examples on this step response. And one more thing is, we can use this relationship between the impulse response and step response to express any of them. That means, if you want to express the impulse response in terms of step response, how we can do that? So, the relationship between impulse response and step response. So, how we are going to get the relationship here is, so in terms of discrete time, as it is mentioned, the step response is the running sum of impulse response. So, if you invert this relationship, then you will can express h of n, impulse response, in terms of step response by this way: s of n, s of n minus 1, and so on. Okay. And if you go for continuous time, now you can see this s of t is the integral of h of t. Then h of t will be the invert operation, that is the differentiation of step response, d by dt s of t. So, we can invert this relationship between the impulse response and step response. Okay. So, let us take some example on step response here. So, first one, so it is a problem given: evaluate step response of an LTI system So, this LTI system is represented by impulse response h of n is equal to 1 by 2 to the power of n into u of n. Okay. H of n is equal to 1 by 2 to the power of n into u of n. Now, you can represent this h of n graphically. So, it will be better if you express this graphically, you will be having some imagination or clear idea about how the signal is. So, u of n is there. So, that means the signal is present only for values of n which are greater than or equal to 0. Okay. Now, if I apply these values for this, and see, if I apply 0, you will get 1 by 2 to the power of 0, that is 1 here. Next, if you apply 1, there is 1 by 2 to the power of 1, 1 by 2 here, then it will be 1 by 4, 1 by 8, and it gradually decays. So, this is how our h of n will look like. This is just for your imagination now. Now, from the definition, the step response is given by summation k is equal to minus infinity to n h of k. Okay. Now, based on this, looking at the signal, so n varies from minus infinity to plus infinity, or the signal should be between this minus infinity to n here. So that means we have to consider uh, both the condition. That means for values of n which are less than 0 and values of n which are greater than 0. So let's see what happens now. Now substitute this k is equal to minus infinity to plus infinity. What is h of not infinity? I think it is n. What is h of k? So h of k is 1 by 2 to the power of k into u of k. So based on this, we have u of k here. So u of k is 1 for k greater than equal to 0, and it is 0 for k less than 0. Okay. So that means it is present only for values of k which are greater than 0. Now coming to this, we are to express in terms of S of n. So that means in the first case, if you look at the signal, for values of n which are less than 0, there is no signal exist. So that means our S of n will be 0. So the first case, case 1, for n less than 0, S of n is equal to 0. Why it is 0? Because h of n is present only for positive values of n. Because h of n is present only for positive values of n. Okay. So this signal is your reference. You can take like this. And given also 1 by 2 to the power of n into u of n. So u of n is present for only positive values of n. Therefore, h of n is also present only for positive values of n. Based on this, we can write for n less than 0, S of n is 0. Going to the second case, for n greater than or equal to 0. So for n greater than or equal to 0, as you can see this, the limit now here it is from minus infinity to n here. This limit now will changes, because from minus infinity to 0 or less than 0, like minus infinity to minus 1, everything is 0 here. So the limit now will be summation k is equal to 0 to n 1 by 2 to the power of k into 1. Why I have written 1? Because u of k will be 0 for this value, or you can neglect this part and you can only stick to 1 by 2 to the power of k. So from geometric series, we have something like this, a relation n is equal to 0 to n a to the power of n. If you have something like this, then it will be e to the power of n plus 1 divided by a minus 1. Now, if you compare this, we have k here and n here. So in place of capital N, we have small n here. So this suits better. We can apply this here. In place of a, we have 1 by 2. So let's applying this 1 by 2 to the power of here capital N is there. We have small n. So write it that one, minus 1 divided by 1 by 2 minus 1. Okay. So you can go for further simplification, like 1 by 2 n into 1 by 2 minus 1 divided by 1 by 2 minus 1 is minus 1 by 2. So you can take 2 to the numerator, minus 2 into 1 by 2 to the power of n into 1 by 2 minus into minus 2 into minus 1. So you can cancel this. So you will remain with minus 1 by 2 to the power of n, and minus into minus becomes plus here. Okay. I think I will directly write this one like minus 2 into minus 1. That becomes plus 1. So if you simplify this, you will get 1 minus 1, sorry, not 1, 2 into 2, right? 2, right? 2 minus 1 by 2 to the power of n. So this is what you are going to get for this. Now you can summarize this. S of n is equal to 0 for n less than 0, and S of n is equal to 2 minus 1 by 2 to the power of n for n greater than or equal to 0. So this is the solution for the problem here. So take one more problem here. So given h of n is equal to delta n plus delta n minus 1. So find step response. Okay. Now observe this, the given signal is the sum of two impulse response, and to be very precise, the signal will look like this. Delta n is present at the origin with amplitude 1, and delta n minus 1 is time shifted to this with amplitude 1. So this is what your h of n will look like. Now based on the definition, we can write k is equal to minus infinity to n h of k. Now if you substitute h of k here, k is varying from minus infinity to n delta k plus delta k minus 1. Now we observe the signal uh, for these values, whatever n value will take, we have to substitute based on that. So based on this, the first case is for n less than 0. If I put negative value for then, I will get k as, since the signals are present only at these two values, so no need to expand this. So it is for, I have to check for negative values of n and positive values only. So for n less than 0, S of n will be 0. You might be wondering why. We have a look here. So if you take n less than 1, less than 0, say if you substitute to minus 1, so your expression will be delta minus 1 plus delta minus 1 minus 1. So you will get delta minus 1 plus delta minus 2. As you can see, we have no signal here. So that's why your S of n will become 0. No signal means for negative values we don't have nothing here. So if n takes negative value, we don't have a signal here. Now n is present only for n is equal to 0 and n is equal to 1. So based on this, we can write the next part for n is equal to 0. For n is equal to 0. So what happens to this? So S of n is equal to delta 0 plus delta 0 minus 1, or you will get delta 0 plus delta, simplifying this, you will get delta minus 1. So delta minus, we don't have anything, at delta 0 we have 1 here. So therefore S of n is equal to 1 for n is equal to 0. Next, for n is equal to 1, because the signals are present only for these values n and n minus 1, 0 and 1. So then what happens to S of n? So elaborate this. S of n is equal to delta 1 plus delta 1 minus 1. So at delta 1 plus delta 0. So we have these two signals at 0 and 1. So what we get? 1 plus 0. So you can say that 1 plus 1, that is equal to 2. So you can conclude like this. S of n is equal to 0, or you can just leave it as it is, no issue about that, because the signal is present only for n less than 0, n equal to 0 and n equal to 1. So only for these values we can substitute. And if you want, what if n takes, because it is varying from minus infinity to n, you can be wondering what if n takes some positive values which are greater than 1. You can try that, but let's see. If I go for n is equal to 2, so we will get s of n is equal to delta 2 plus delta 2 minus 1. Okay, you might end up with the value here, but as per the signal is given, it is present only at 0 and 1. So for n less than 0, everything is 0. And for n equal to 0 and n equal to 1, we have the values 1 and 2. And for greater values, I think this is no need to calculate for that one. Okay. So this is for the second problem, delta n plus delta n minus 1 here. Now let's take one more example here. Given h of t is equal to t square u of t. So for this what we have to do, find step response. Now it is a continuous time signal. Let's have an idea about how the signal will look like. Now you observe this u of t is there. So u of t means it is present only for positive values of t, and the t square means whatever the value you are going to apply here, so it will take the square of it. So for 1 it will be 1 here, and for 2 it will be 4, and for 3 it will be 9, and for so it will be 16. So it will keep on increasing. It's a ramp function. It will keep on increasing like this. Okay, so this is t square u of t. So it's amplitude 1, 4, 9, and so on. So this is just for your imagination. This is nothing but a ramp function. Okay. Now, if you observe this, for values of t which are less than 0, there is no signal exist. So that means the signal, the step response is 0 for this particular duration. And if you don't want, you can forget that. You can apply only for values which are present. So s of t is equal to integral of minus infinity to t h of tau d tau. Okay. Now this value minus infinity to t, so this value, let's see, minus infinity to t, h of tau is there. So t square into u of t, I think we have to express in tau here, tau square into u of tau d tau. You can see u of tau is there. So u of tau, it will be present only for tau greater than or equal to 0, and it will be 0 for tau less than 0. So based on this, we can simply write it like this. For case 1, for t less than 0, s of t is equal to 0. So based on this, you can write, because if you substitute the value for less than 0, so this entire signal is 0 here. So therefore s of t will also be 0 here. Okay. Now for values of t greater than or equal to 0, now our limit, it is from minus infinity to minus 1, everything is 0. So the limit changes from 0 to t here. So t can take any positive value. So that's why greater than or equal to 0. So s of t is equal to integral varying from 0 to t h of tau d tau. Okay. Now values of h of tau is integral of 0 to t tau square, and u of t for values of t greater than 0 is 1. So, that is why tau square into d tau. Now, if you integrate this, it will be tau cube by 3, limit varying from 0 to t. So, if you apply the limit, you will get t cube by 3 for this. So, therefore, we can conclude or summarize this way: s of t is equal to 0 for t less than 0, and it is equal to t cube by 3 for t greater than or equal to 0. So, this is a different kind of problem here. Now, I will take one more example here. So, the given signal is h of t is equal to e to the power of minus mod t u of t is there. Now, this signal, it looks very simple, but if you observe this, they mentioned e to the power of minus of t. That means this t, as per the relation or the definition of step response, t varies from minus infinity to t here. So, the limit varies from minus infinity to t means t can take positive values as well as negative value here. Now, if this is modulus t here there, so this t can take positive or negative value because it is put in the mod here. So, what if it takes positive value? If it takes positive value, then the signal will be e power t into u of t. If it takes negative value, then it will be e power t u of minus t. So, these are two different cases here. Now, we have to consider this t varying from minus infinity to t means, so we have to consider the negative value of t as well as the positive value of t. So, we have to express the signal for both the duration here. Okay. So, if you take this h of t, if you plot this, so first signal, if you take the negative axis, u of minus t, so u of minus t is 1 for the negative values here, e to the power of t is there. So, e to the power of t means it is a exponential signal which is increasing. So, growing exponential, you can call this as growing exponential, and another one as decaying exponential because it is e to the power of plus t is there. So, now for this particular duration, we will be having a signal, and at 0 it will take the amplitude 1 here. So, this will be e power t into u of minus t. So, the negative part of the signal. Now, come to this part, this is e power minus t u of t. So, u of t is present for positive values, but that will be multiplied by e power minus t. So, e power minus t is a exponential signal which will decaying with respect, which will decay, which decays with respect to time t here. So, this is how the signal will look: e power minus t into u of t. So, this is how the signal will look like. Okay. So, why we have taken like this means based on the signal, it is given in mod, that means it can take positive values as well as negative values. So, we have applied both and we got this result. So, based on this, the plot is completed. Okay. Now, let us move on to the problem here. So, first case, for case 1, for t less than 0. So, for t less than 0, you observe this is the part here. We have a signal e power t u of minus t here. So, let us go for it. S of t is equal to integral of minus infinity to t h of tau d tau. So the limit now will remains the same because t is only from here minus infinity to t. Okay, that is t as taking the negative value. Okay, so what is the signal we have in this particular duration? What is h of tau in this particular duration? So the value of h of tau is e power tau into u of minus tau. E power tau u of minus tau d tau. Now since it is the negative axis and in this duration u of minus tau value will be 1. Okay, you can cross verify like this. U of minus tau is 1 for minus tau greater than or equal to 0 and 0 for minus tau less than 0. If you simplify this, you will get the limit tau less than 0, tau greater than 0. So now values of this for tau greater than 0, u of minus tau will be 0 and for 1 u of minus tau will be 1 for values of tau which are less than 0. So that's why. So that gives us minus infinity to t e to the power of tau d tau. Now if you integrate this, you will get e to the power of tau, the upper limit and lower limit. So integrate this, you will get e to the power of t and so if you apply the limit e to the power of minus infinity, so that you remains with e power t only. Okay. So this is for t less than 0. Let's take the second case, that is for t greater than or equal to 0. So in this case, greater than or equal to 0, if you take this case here, that means I have to put t somewhere here or at least here. So if this is the case, you observe this minus infinity to t. Now t is somewhere in the positive value here, positive axis. Now in this case, I have to integrate this entire region here, which has two different kind of signals. From minus infinity to 0, we have e to the power of t, u of minus t here, and from 0 to t, I have e to the power of minus t into u of t. So we have to consider these cases, both case, and we have to perform the integration to find the value of s of t. So based on this, for t greater than 0, so s of t is equal to minus infinity to t h of tau d tau. Now this will split like this: minus infinity to 0 e to the power of tau u of minus tau d tau plus 0 to t e to the power of minus tau u of tau d tau. So as these two will become 1 in these durations, so minus infinity to 0 e power tau d tau plus 0 to t e to the power of minus tau d tau. Now if you integrate this and if you apply the limit, so this will be e to the power of tau with minus infinity to 0, and this will be e to the power of minus tau with limit 0 and t here. So if you simplify this, I think you should get 1 here and plus minus e power minus t plus 1, and if you go for the simplification, 1 plus 1 is 2, so 2 minus e power minus t. So this is what you are supposed to get after applying the limit. So therefore, concluding this, s of t will be equal to e to the power of t for values of t less than 0 and 2 minus e to the power of minus t for values of t greater than or equal to 0. So this is the conclusion for this. Okay. And I hope you have understood this method. Anyhow, I have one more problem I will take here. Just I'll conclude this step response by taking this example, and in the next video I will directly move on to continuous time Fourier series. Okay, so there is a impulse response given k is equal to 0 to 2 delta n minus k. So this is what they are given, and the question is find step response. So this is what we have to find here. Now coming to this, we have h of n is equal to 1 by 3, k is equal to 0 to 2 delta n minus k. So this is given. Now apply this value for k. So for k is equal to 0, you will get delta n plus k is equal to 1 delta n minus 1 plus k is equal to 2 delta n minus 2. Okay. If you observe the signals are present. This is impulse function. So this impulse function is present at n is equal to 0, n is equal to 1 and n is equal to 2. So graphically, if you represent this h of n, this will have the same amplitude 1 by 3 at origin, 1 by 3 at 1 and 1 by 3 at 2. Okay. Now this signal we have to find step response, means so for n less than 0. So first case 1, for n less than 0, so our s of n will be 0 because there is no signal exist here. Now in the second case 2, since the signal exists at 0, 1 and 2, we have to just find s of n for only this value. Okay. So from the definition it says s of n is equal to summation k varying from minus infinity to n h of k. So that gives k is equal to minus infinity to n 1 by 3 into delta k plus delta k minus 1 plus delta k minus 2. Okay. Now you have to apply the value, you can apply the value for n only at 3 instances, that is at 0, at 1 and 2. So therefore s of n is equal to, first I will apply this one. For n is equal to 0, so s of n is equal to 1 by 3 into 0 is there. So that means delta 0 plus delta minus 1 plus delta minus 2. So that means 1 by 3, the signal is present only at this point. The value will be 1 by 3 here. Next, n is equal to 1. S of 1 is equal to 1 by 3 delta 1 plus delta 1 minus 1 is 0 plus delta minus 1. Now this 3, here no signal exists, so you will remain with 1 by 3 into delta 1 plus delta 0. So that means it is 1 by 3 plus 1 by 3, that will give you 2 by 3. Next, last, at n is equal to 2, for n is equal to 2, s of n is equal to 1 by 3 into delta 2 plus delta 1 plus delta 0. So that means 1 by 3 plus 1 by 3 plus 1 by 3. You might be wondering why I have not multiplied this, because delta 2, delta 1 and delta 0. So, the value of these three are 1 only at their respective points, which is multiplied, which is scaled by scale factor 1 by 3. So, we have to add these three here. So, that will give you 3 by 3, which is equal to 1 here. So, this is the solution for this problem here. Okay. Now, I hope you have understood what a step response is and how to find the step response for a given signal. So, for step response, the input should be a unit step function, then only the output will be a step response here. And the impulse response will always be expressed in terms of unit step function only, most of the case you can see that. And step response is also called as the running sum of impulse response, which is evident by the problems that we have solved in this video. Hope you have understood this method. If you have any queries, do reply or comment in this video. Thank you.